Hi everyone. In this video from Count Backwards from 10, we're going to take a look at how to calculate the amount of oxygen and nitrous oxide left in their respective tanks, as well as discuss how to go about figuring out how much longer you'll have with the current tank at a given rate of delivery. This is pretty high yield. You're going to see a question in your exam, be it the ITE, boards, whatever it is, it's going to come up. It's easy points. And we're going to do this now, go through it very quickly, easy ways to calculate it for both oxygen and nitrous oxide. And it's important that we go over both of them because they're different. Now, before getting into specifics, we first need to understand the difference between the types of gases that we store in our cylinders. There are two types, and they're referred to as our liquefied and our non-liquefied gases. And basically what these means is that a non-liquefied gas means that at room temp, no matter how much you compress it, you cannot make it a liquid. Cannot make it a liquid. And I'm just going to draw an X through it. But a liquefied gas means that at room temperature, it can be compressed enough to make a liquid. And the examples that we're going to use here for this, like I mentioned before, are going to be nitrous oxide and oxygen. And they're going to be the two that we talk about here in this video. Now, whether it's liquefied or non-liquefied is important because it has implications as to being able to determine how much is actually left in the tank. So let's go ahead and start with oxygen, one of our non-liquefiable gases, denoted here as O2. First, we need to know how much oxygen in liters, and we're going to use our E cylinder in this example, and also for the nitrous oxide, that tends to be the transport tank. And an E cylinder of oxygen has 660 liters, and it's pressurized to 2,200 pounds per square inch, or PSI. So this is going to be our conversion factor basically all the time when we're dealing with calculating our oxygen, how much is left in the tank, etc. Now, using this, we can basically answer any question that's thrown at us through the use of simple dimensional analysis. So let's take a quick run through of an example. Maybe they'll ask how much oxygen is left in the tank if the pressure gauge reads 100 PSI, and they want to know, like I said, how many liters. So like I said, we're just going to use our conversion factor here, and 660 liters over 2,200 PSI is equal to X liters over 100 PSI. So we'll go ahead and turn that into 660 liters times 100 PSI is equal to 2,200 PSI times X liters. We'll divide both sides by 2,200 PSI. The units will cancel. That leaves now X liters is equal to 66000 over 2,200, which leaves us with a total volume left of 30 liters. Super easy to go through. Our units cancel appropriately. Now we just want to take a quick look and just have an idea, ballparking, if our answer is, correct, without going through the math again, just to double check yourself. So to get 10% of any number, we're just going to move our decimal point 1 to the left. So if we have 10% of 660 liters, which would be 66 liters, 10% of 2,200 PSI is 220 PSI. So what this means is that 220 pounds per square inch, we should have 66 liters left in the tank. And so in this case, we're saying we have about half of that PSI, 100, and we have 30 liters. So just getting a rough estimate to make sure that our numbers make sense is always important. Or you could get caught, you could have a wrong decimal point, and it's an easy equation to throw away on a test. But worse, in real life, you not just might get the question wrong, but maybe you think you have more time than you actually do with an oxygen tank or something for transport, etc. So super easy way to go through this, figure out how much oxygen is left in your tank. Now, the other kind of question you may be asked is, well, if the PSI reads 1100 and you have a flow rate of 3 liters per minute, how long will the tank last? That's also going to be another kind of question that's going to come up in your exams. And again, we're going to go ahead and use our dimensional analysis skills and say that we have 1100 psi. Then we'll use our conversion factor times 2200 psi on the bottom, 660 liters at the top. And then again, another conversion factor, because we said that we're running this at 3 liters every 1 minute. So just like before, our PSIs are going to cancel, our liters are going to cancel, and this leaves us with minutes as our unit. And without doing all of the math here, I'm just going to go ahead and tell you that the total at the end is 110 minutes, or just under 2 hours. So super easy to calculate how much oxygen you have left, super easy to calculate how long it's going to run for. These are gimme points on tests, and I hope all this made sense. So I'm going to go ahead and erase all of this. Sorry, that was definitely not the eraser. And now we're going to talk about nitrous oxide, and we're going to do that in blue, so we have like a pretty distinct difference over here. Let me go ahead and redraw that line. So as I mentioned before, nitrous oxide is a liquefiable gas, and this is where things are a little bit different. Now, we're not going to cover the whole dimensional analysis again in order to answer these questions, because it's going to end up being the same, but there is something, like I mentioned, a little bit different about this because of the liquefiable portion of it. So, as I mentioned earlier, there are liquefiable and non-liquefiable gases at room temperature, and this is one of them. So, if we have this nitrogen tank, with the release at the top, nitrous oxide tank, and we have liquid in here that's all nitrous oxide. There's also some amount of it that's floating around in the tank as gaseous phase molecules of the nitrous oxide, and this goes until we have equilibrium of molecules leaving the liquid phase, entering the gas, and leaving the gas to enter the liquid phase. Now imagine we open the tank to allow some of the nitrous oxide to leak out. As this happens, more molecules of the nitrous oxide than in liquid phase will now join the gaseous phase in order to replace the molecules that left. As a result, it's very important to note that the pressure is not a reliable way to determine how much is left in a nitrous tank, because so long as there is liquid nitrous oxide to replace the volatile gas that left, the pressure will always remain 750 psi, always, until we are at less than 1/4 of a full tank, and this is when there is no more liquid nitrous oxide left. There's no more liquid nitrous oxide to replace the volatile as it leaves. Now, a normal full E cylinder of nitrous oxide is going to contain 1,600 liters, which means that at 1/4 total volume, at 400 liters of nitrous oxide, you will then begin to see a drop in pressure. And this is very important because it means that for any reading of 750 psi on the nitrous oxide tank, it is impossible to know how much is actually left, strictly with math. Instead, what we can do is we can weigh it, and a full tank weighs, an E-tank, 8.8 kilograms. And what we can do is we can weigh our new tank and compare that to the weight of a full tank to decide how much is left. So the take home for this part is that until we are at less than 1/4 of the total volume inside the tank, the pressure will not change. That's all for how much is left in the tank. As always, if you have any questions or concerns, please feel free to write in. Hit the like button below, subscribe, follow us on Instagram at Count Backwards from 10, and stay tuned for the next video.